are covering, or rather continuing in chapter 11 today. We are, or rather the kind of goal and the topic is looking at different measurements that analyze probability distribution. So the lesson 11.3a that we covered right before the quiz was actually identifying random variables and then making a probability distribution for a random variable. And then this is a next step of actually analyzing that distribution with the mean, which is actually called the expected value. So if a question asks you for the expected value of something, it's asking for the mean, which is actually going to be a weighted average in this case. And then also looking at standard deviation, which could be used to compare two different distributions that might have the same expected value or expected outcome. So I just have, there's 3 examples, and then you should have some time to work before we're done with class today. And then I don't see you guys tomorrow. I'll see you again Thursday, so then Thursday we would go through and actually correct this before we move on. But what I have included up at the top here is that probability distributions are often used to analyze financial data. Not that that's the only time they're used, but often used for financial data. The 2 most common statistics used to analyze a discrete probability distribution are the mean, which, as I said, the mean in this section is going to be referred to as the expected value because it's a weighted average and not just the average, and then the standard deviation. So the expected value, which they're going to represent as capital E of x. So x is representing a random variable, and again, a random variable is the numerical outcome of some event. So E of x would be the expected value of that random variable, the expected outcome. And the expected value of a discrete random variable of a probability distribution is the weighted average of the variable. And then in this box here, it's explained how to calculate it, and then we'll go through a couple of examples of actually calculating expected values. So in this box, it says in words and then also in symbols, and I'll talk a little bit more about the symbols that you see. So the expected value of a discrete random variable is the weighted average of the values of the variable. So this might be something you want to make note of just in words so you understand what this represents. It is calculated by finding the sum of the products of every possible value of x and its associated probability p of x. So that is actually represented here, that E of x is equal to this symbol in math represents, it's called a summation, but it represents a sum. So this is saying you take every possible outcome for x, multiply it by its corresponding probability, and then you add all of those products together is what that represents. So you'll see, actually, if you look at example 1, this type of table, we're actually missing the probability row from this table, but this is the type of table that we actually set up in 11.3a. where you had to come up with what are the possible, or what is the sample space. So in this case, it's talking about values of winnings for a ticket. And then we had to find those possible sample space outcomes, find the frequency of each outcome, find the probability then of each outcome, or that relative frequency. So this is just building on what we had done in 11.3a, except you might already be given the table or part of the table that we had worked on setting up in that lesson. So in example 1, it says Kurt won a ticket for a prize. The distribution of the values of the tickets and their frequencies are shown. Find the expected value of his winnings. So thinking of how this could be helpful information, so if there's a ticket that could win a prize, what you're seeing here, these are the expected values of the winnings. So you could win anywhere from, or you could win $1, $10, $100, $1,000, $5,000, or $25,000. This is the frequency of each occurrence, each value's occurrence. So then what we would need to find before we're able to calculate the expected value is the probability of each value. The question, though, is, so we want to know, say, winning a prize of $1. What is the probability of winning a $1 prize? So how would we calculate that probability? Or think back to lesson 11 3A when we were making these tables ourselves. How did we calculate that relative frequency or the probability?
Isn't that long table where you go like, you take all the top numbers and then you go to the top and then you also have it at the side too?
So that's how, yeah, that's how we had come up with, that's how we had found the frequencies of all of them. So that's actually filled in for us already. So once we had the frequencies, then how did we calculate the probabilities is what I'm asking. Or what information would we need to know in order to calculate probability? Pardon? So like the total possible outcomes. From the information we have, how could we find the total possible outcomes? Yes, so we can add all of these frequencies together just to see what are the total number of outcomes that we have. So if we add 5,000, 100, 25, 5, 1, and 1, I'm getting 5,132. If you want to label this total possible outcomes. Because then probability is frequency divided by the total possible outcomes. So taking the frequency that it could occur and dividing it by all of the occurrences to get that percentage. And now these, I'm fine if you write them as decimals. However, only if the decimal is a terminating decimal. If you get a repeating decimal, leave it as a fraction. So this probability, for example, would be the frequency 5,000 divided by 5,132. And so I could actually check that if I take 5,000 and I divide by 5,132, I get this long decimal that tells me this is a repeating decimal. So I'm going to leave that as a fraction and not round the decimal. Because if I round this, that's going to throw off my answer in the end. Nothing should be rounded until the very end of the problem. So that probability is 5,000 over 5,132, meaning the probability of winning $10 would be 100 over 5,132. And even though these fractions, I will just say I know that I can simplify these, but since the probabilities aren't my final answer, you don't have to spend time simplifying these unless you wanted to. You can leave them because we're just going to be using them in a separate calculation. This isn't part of our final answer. So the table itself was part of your answer in the previous lesson, which is why I wanted you to simplify them. Here it's fine if you don't simplify in this step, just as long as your answer is in simplest form. And then the probability of winning $100 would be 25 out of 5,132, and then so on. So probability of winning 1,000, 5 out of 5,132, and then the probability for winning 5,000 and 25,000 are actually the same, 1 out of 5,132. So that's your, I guess if we actually divided these, you can actually see still from when I calculated that. So you have just above, you have about a 97.5% chance of winning $1, meaning the remaining 2.5% of your chances are winning $10 or more. But 97.5% chance that all you're going to win is $1 is what that would mean. Okay, so then where we're headed with this in this section, what's new, is to find the expected value, which we can write as E of x. What this means is Kurt can calculate the amount of money he should expect to win. So these are the different probabilities of the different winnings, but he can calculate what he would expect to win, which is going to be the weighted average of each value and their probabilities. So to calculate this, what you do, and if you look at this calculation just to make sense of it, all of these values here, this top row, these are your different values of your random variable x. And then the probability row, this is P of x, the probability of each value. So you take each value, each winning value, multiply it by its probability, and then you add all of those products together. So if we write the whole thing out, it'll look like this. To win $1, that probability is 5,000 over 5,132. So I multiply that probability by 1, and then I add to it $10 multiplied by its probability of 100 over 5,132, plus for $100, I multiply 100 by its probability, 25 over 5,132, plus to win $1,000, multiply that by its probability, 5 over 5,132, and then same thing for 5,000 and 25,000, so 5,000 times 1 over 5,132, and then 25,000 times 1 over 5,132. And so all of those get multiplied and added together, and then our answer is the expected value. And I'm going to show you, just because we were leaving these as fractions, how I would recommend typing this into your calculator, not that it's the only way. There's other ways you could simplify this expression to get the actual value. But the way I would type this in probably would just be kind of exactly how it looks, but I realize some of your calculators work differently, that you can't just type in one long string. So if you are, I would recommend typing this into the calculator you have and making sure that you can get the right answer on your calculator. That's what's important, is that you are able to get the right answer. So I would just type it in as 1 and then times, in parentheses, 5,000 divided by 5,132, close the parentheses, and then plus, and so on. So then plus 10 times, in parentheses, 100 divided by 5,132, close the parentheses, plus 100 times, in parentheses, 25 divided by 5,132, and so on here. Okay, and then if you look up here, this is what you should get as an answer. This is the correct answer. And here's where, if you're not able to get this on your calculators, I guess if you're not able to get this, just make a note when you have time to work. Let me know, and I can look at your calculator and maybe see how you're typing things in, and help you so that you're not getting wrong answers when you take an assessment on this. Okay, but here's the answer. Now the question is, what should we round to? So what are the units going to be on our answer in this problem? What units will our answer have? Nobody has an, oh, Cora? Dollars, yes, thank you. So if it's dollars, round to the nearest cent. So he should expect to win $8.48. Now, I will say the expected value may or may not actually be a possible value. So if you look at the possible winnings, it's not possible for him to win $8.48. That's not an option. However, this is the correct expected value. So he would probably look at this expected value and say, okay, it's expected that I'm either probably going to win $1 or $10, but it's obviously not expected. It's going to be a very rare chance of him winning the $25,000. Okay, any questions on that one? Okay, so then I included a second example of just finding the expected value. This one doesn't give you a table that's already set up. So this one is talking about a tetrahedral die that has 4 sides, numbered 1, 2, 3, and 4. And it says find the expected value of one roll of this die. Okay, so here we're not given a table that has the possible values, the frequency, the probabilities, so I'm going to set that up. So I already am given, if I have, I'm just going to put X here. So X, again, is representing the numerical outcome. So if I roll this die, I'm either going to get a 1, 2, 3, or a 4. So my possible values for X are 1, 2, 3, or 4. Just kind of setting up a table here. And then I want to list the frequency of each of these outcomes occurring. And if the problem does not specify anything about if it's regarding a die or dice, and if it doesn't say anything in the problem about them not being fair, we're expecting that this is a fair die that we're rolling. So I would say we have 4 different outcomes. We could roll a 1, 2, 3, or 4, and we would expect if we rolled the dice 4 times, each time they're going to have the same frequency. So the only possible values to get are 1, 2, 3, or 4, and they would each have the same frequency. Again, this is expected. Obviously, if you rolled it 4 times, you may not get each number once. But then probability, or P of X, would then be this frequency would total to 4, and you could probably even jump straight to the probability in this case. So if you have 4 different sides, each side would have an equal chance of occurring. So each side is going to have a 25% chance of occurring. So each of these is 1/4, or you could write that as 0.25 if you wanted to write the decimal for these. So 1/4 or 0.25. Each side has the same probability of occurring when you roll it. 25% chance for getting a 1, 2, 3, or a 4. Normally, if you have a problem that deals with die or dice and it's not a fair die, they will actually give you the frequencies already. So then from here, if we were to calculate the expected value of a roll, so we're calculating E of X. Again, we take each value and multiply it by its probability. So chance of rolling a 1, I multiply that by 0.25, plus the chance of rolling a 2, multiplied by 0.25, plus chance of rolling a 3, multiplied by 0.25, plus chance of rolling 4, multiplied by 0.25. And if I take each of these numbers and multiply it by 0.25, I end up getting an expected value of 2.5. Okay, so as I said in example 1, your expected value may not be an actual outcome. It's a weighted average. So obviously it's not possible to roll a 2.5, but that is the expected value, the expected outcome. Okay, and in the next example, we're going a step further with this and looking at standard deviation. And then with that, we're also looking at comparing two of them. So this is just kind of seeing one measurement we could take. You'll kind of see when we start to compare, the expected outcome might start to make a little more sense. Cora, you had your hand up. So it is saying the expected outcome would be a 2.5. Now, this is the correct value. Oops. But yeah, in looking at this, obviously you can't roll a 2.5, but this is just saying for each of the possible outcomes and their probabilities, this is what would be expected as a weighted average. So I included this example. It is different from this one, but this is also why at the beginning it said these are often used to analyze financial data, because I'd say with financial data, the expected outcomes tend to make a little bit more sense with that application. However, you can apply the expected value calculation to really any discrete distribution. But yes, this is saying you would be expected to roll a value of 2.5, even though that's not possible to do. That would be the expected value. Did you have the same question? Okay.
I thought I only had Mrs. Schmidt, and we usually have possible now, and she said that would be fine if I took my math.
Okay, so do you want to take it third hour instead?
Otherwise, I could take it to the library too. That's where we are right now.
Okay, because you could at least see the rest of this lesson and then just take it third hour. Okay, so here we're going to go back to an example that deals with money. Those tend to just make a little bit more sense when you're getting your expected value. And then, like I said, we're also expanding this, talking about the standard deviation and then the comparison, so you can kind of see if this was even calculated, then what it's used for, since you're not necessarily seeing what it's used for just by calculating an expected value. So we kind of talked about this similar information. I know it was the day I was gone, but when you just calculate a mean, it says sometimes the expected value, which is that weighted average or that mean, it doesn't provide enough information to fully analyze a probability distribution. So it says, for example, say you had, it's talking about spinning two different wheels for a prize, and say they had roughly the same expected value. It says, which one would you choose then to spin? Or, like the example we're going to look at, say there's two different raffles you could enter into, and they have the same expected winning amount. If they have the same expected winning amount, which one would be better, or would be better for you to enter into? Which one would give you a higher chance of winning something if the expected value for both is the same? Because just because the expected value is the same doesn't mean everything else about the two would be the same. So this is where you kind of look at which one would be riskier, especially if it deals with, maybe spending money to buy a ticket to try to win something. Which one are you going to want to spend your money on? Which one gives you a higher chance of winning? So this is where you can actually find the standard deviation to help out to make comparisons. The standard deviation can provide more insight into the expected value of a probability distribution. So it does give the formula for calculating the standard deviation in this box, and it is a similar calculation as the one that you had on your quiz, the one we went through with just regular standard deviation. So you first have to calculate the variance. So it says in words, for each value of x, you subtract the mean from x and you square the difference. So for every value, subtract the mean or the expected value and square it. And then with those new values, you calculate your mean or your expected value again. So then you take all of those new values and multiply by their corresponding probabilities. and you add all of those products together, and that is the variance. And then the standard deviation is the square root of the variance. So it is also giving that in symbols. So it's showing, again, you're taking a sum of each value subtracted by the mean squared and then multiplied by the corresponding probability. And then the standard deviation is the square root. So we're going to look at how to do this, but again, if you remember calculating the variance and standard deviation on your quiz, it's a similar calculation, but it also ties in the calculation we just did for expected value on the front. So for example 3, we have, at a raffle, 400 tickets are sold for $1 each. So we have 400 tickets sold for $1 each. This the price of a ticket, that's going to be important when we're calculating here. And 1 ticket will win $100, 5 tickets will win $10, 10 tickets will win $5. Calculate the expected value and the standard deviation of the distribution of winnings for a $1 ticket. So again, this is a problem we are not given a table of the possible values and then their frequencies to then calculate the probabilities. We're going to be calculating the expected value first. So I'm going to set up a table. My possible values for x are going to be, when you buy a ticket, the outcome of the winning. So looking at this, it looks like it's possible to win $100. So 100 would be a value of x. It's possible to win $10. And it's possible to win $5. And then it also gives those frequencies because it says only 1 ticket is going to win $100. So the frequency of getting $100 is 1. 5 tickets will win $10. And then 10 tickets will win $5. Now, the problem did tell us that there are 400 tickets sold, meaning all of our frequencies should add to 400. But if you add 1, 5, and 10, that's only 16. So that means there's a remaining 384 tickets that would win what amount? 0. Okay, so of the 400 tickets sold, only 16 tickets are actually going to win something. And then 384 of those tickets win nothing. So even though it doesn't say up here 384 tickets will win $0, you're inferring that from the problem, making sure all of your frequencies do add to that total amount. So this would be our table here. And then we know this totals to be 400. So then we can calculate our probabilities, P of x. And we should be able to use decimals here. So if we divide the probability of winning $100, we take 1 divided by 400. So that probability as a decimal is 0.0025. And then probability of winning $10, divide 5 by 400. And that's 0.0125. To win $5, divide 10 by 400. That is 0.025. And then dividing 384 by 400 gives us 0.96. So there's a 96% chance that you won't win anything with this particular raffle. Okay, but we can calculate if somebody is entering into this raffle, what could they expect to win monetarily. So we're going to calculate their expected value, just like we did on the front. So take each amount, each value of x, multiply by its probability. So we would multiply 100 by 0.0025, and then plus multiply 10 by 0.0125, plus multiply 5 by 0.025, and then I'm still going to write it out, but I know 0 times 0.96, that's just going to be 0. Now, one thing I do have to add to this expected value calculation that I didn't have to add to the either example on the front is the expected value is what you would expect to win. However, you have to remember that you are paying $1 to even enter in to this raffle. So your expected winnings should not include the amount that you had to pay. So I would then take this weighted average, but I would have to subtract 1 because the 1 is the cost of even entering into the raffle. So if you have a problem that involves some sort of cost like that, that does need to be subtracted from your possible winnings. Okay, so if I actually calculate this, I end up getting the expected value is negative 0.5, meaning it's a negative 50 cents. Okay, so to make sense of that, you would expect by entering into this raffle to lose 50 cents. That's what that means. Okay, so really, I guess you could look at it this way. You're looking at earning 50 cents, but since you're paying $1, you're really at a 50-cent loss. So that's what is expected. And that's partially, well, really due to the such high probability of winning nothing. But now what I can also do, since I found that mean, or that expected value, is then calculate the standard deviation. And the standard deviation, again, would show the spread of this distribution, which would show if values are very spread out, it would show there's really great variability in your winnings or your losses. So to calculate that, what I'm actually going to do is calculate the variance first. And to do that, I'm just going to write off to the side, I'm going to calculate what my new values are. So if you think of calculating variance, what you would have done on your quiz, I have to take each of these values of x, subtract the mean, which is e of x, and then square it. So I'm going to come up with what my 4 new numbers here would be. I'll write it like this so you can see where the values are coming from. So take each value of x, subtract the mean, which is e of x, and square it. And I'm going to write what those 4 new numbers are underneath. So if I take, I'll do in parentheses here, if I take 100, and since I'm subtracting a negative 0.5, I'm really adding 0.5. So I have 100 plus 0.5, and then I'm squaring that. So that new value is 10,100.25, and I'll do the same thing for the 10. And that would be 110.25. And do the same thing for 5. And that's 30.25, and then same thing for 0, which is just 0.25. Okay, so again, take each value, subtract the mean or expected value, square it. So I have 4 new numbers. And now, to find the variance, which again, if I'm trying to tie in the notation that's given above, the variance is that sigma squared. Okay, so the variance then is taking each of those new numbers I just got in my list and multiplying them by the corresponding probabilities. So when I look at this, just because I do have them written in order, like this value came from using the 100, so I would take this value and multiply it by the probability of getting $100. So I'm it's like I'm calculating a new expected value. Except I do not have to subtract the cost for this one. So I would take the 10,100.25 and multiply that by the probability of getting 100, so 0.0025. And then I would take the 110.25 and multiply that by the probability of getting a 10, so 0.0125. And the 30.25, multiply that by the probability of winning $5, so that was 0.025. And then take the 0.25 and multiply that by the probability of winning nothing, which is 0.96. Okay, so when I add all of those products together, and I would recommend you make sure that you can get the correct value using your calculator as well. I'm getting 27.625. So again, any of these calculations, if you're not able to get them, they're not working out that way in your calculators, please let me know once we wrap up these examples here. So then the standard deviation, which is going to just be sigma, it's the square root of your variance. So we would then take the square root of 27.625 and again, the square root is, or the standard deviation is also going to represent money, so rounding to the nearest cent. So you should get approximately $5.26. Now, standard deviation, I feel like as we move through this chapter, it becomes easier to understand because we actually look at distributions and how the standard deviation really fits into your probability of earning something. So aside from explaining just this number here, I want to look ahead to example 4 so you can see the importance of actually calculating the standard deviation. So we have the expected value of this raffle with the standard deviation. And if you look at example 4, because it ties in, it says a second raffle has the same expected value as the raffle described in example 3, but has a standard deviation of $1.32. Which raffle would you recommend someone participate in and why? So this is where standard deviation is helpful when you can kind of compare. It's usually used if two different data sets have the same mean, or in this case, the same expected value. So there's two raffles. You go somewhere. There's two raffles, same expected value. You want to know which one then should you enter in to give you a higher chance of actually winning something. So what this would mean is you'd want to choose the raffle that has the smaller standard deviation. So I'm going to put here, and I'll explain why. I'll put here, I would recommend the second raffle. And then I'm going to add in there, the reason you want to choose the one with the smaller standard deviation, the smaller standard deviation means there would be less risk. So yes, if you entered into that first raffle, because the standard deviation is higher, that means even though it's more risky, you could potentially end up earning more money, or you could potentially, it could go the other way, you could potentially end up losing more money, versus this would be a less risky bet, so your gains might not be as high, but also your losses wouldn't be as low. That makes sense. So the smaller standard deviation just means all of the winnings and losses, the data is less spread out. So if you were to either win or lose, It's less of a risk because your winnings or losses would kind of be closer together. You're not necessarily going to earn a ton more money, but you're also not going to lose a bunch of money. Versus this one would be a little bit riskier. So that's really kind of looking at that value, what that would be interpreted as. So I'm going to put here the smaller standard deviation makes it less of a risk to lose money. So again, I know it said at the beginning, a lot of the expected outcomes or expected values are tied into financial distributions that do with money. And that's where looking at standard deviations, you're looking at when you compare two things that would be more risky, would be a common application from this.